In this section, we're going to look at nuclear physics math and some of the decay reactions and do a little bit of math with it. And we'll do this graphically and we'll add some equations to the mix. Often you can do both. But before we start, let's go ahead and just get a little review of the last lesson. Here's an example where lead is going through, and you should be able to recognize this. This is going to be beta decay. You have an electron being given off, leaving a proton as a result. So therefore, when you're balancing it, 209 plus 0 equals 209. 83 plus negative 1 equals 82. And then you look off the periodic table, 83 is a bismuth, Bi. So it's a balanced equation. This is beta decay. Answer that. What particle is given off? What particle is given off during alpha decay? So this is a different question. If it was alpha decay, it would be 42He, a helium atom. And then beta decay, back to this one above, it would look like this. Remember the symbol. Alpha is that, beta is this. So a little bit more about half-lives. Half-life is the time it takes for half of something to decay. So if you had 100 grams of something, one half-life, you would have, after one half-life, you'd have 50 grams. It could be from seconds to billions and billions of years. And there's often decay constants that relate to how fast something would decay. So just looking at this graph, you have it in your notes just to finish it off. At 0 time, you have 100% remaining, or a fraction of 1. And as you go down, you go 0.5, 0.25, and just keep on cutting it down. So you get 0.25 divided by 2. If you don't want to think, you just type it in the calculator, divide by 2. 0.125 divided by 2. 0.0625 divided by 2. And at that point you have 0. I really should have wrote a 0 at the beginning, so you can. It's easier to see a decimal place when you write a 0 first. Is 0.3125, and so that's fraction remaining. And the fraction decay would just be whatever that number is minus 1, or 1 minus that number. And so therefore here you'd have 0.5 decayed. Here you'd have 0.75 decayed. Here you'd have 0.875. And then you have 0.09375. And you get 0.9. You get 6, 8, 7, 5. And so combined you're going to have 1, or 100% of the initial sample. And then all you have to do for the sample size, it's kind of the same deal, 50 grams. If you had 100, this is at time 0, 100 at time 0. After one half-life, you have 50 grams. 2 half-lives, 25 grams. 3 half-lives, 12.5 grams. 4 half-lives, 6.25 grams. And you keep on going, 3.125 grams. And I'm not going to finish this whole thing off, but if you're trying to figure out how much decay, you're just doing the opposite. 100 grams minus 50 would be 50. 75 here. 100 minus 25, 75. 87.5 here. So just take 100, go to the 100 gram sample you start off with, subtract whatever you have here, and this is what you're left off with. If you knew the fraction remaining, you would just multiply it by the gram sample that you had in the first place, and you would get this amount right here, how much is left. So here are two half-life equations if you don't want to go ahead and do a table for everything. These will often save you some time. The fraction of radioactive material left, that's the symbol Y here, is equal to 1 over 2n. Now n is the number of half-lives. And then another variable you're going to use over here is just half-life time. How long would one half-life be? Well, if you knew the time, and you knew how many half-lives occurred in that time, you could figure out that t equals 1/2. And you might need to do a little rearranging, like n equals t over t 1/2. Any sort of rearranging with these formulas. So let's go ahead and look at a couple of problems. Here is a simple problem. How much of the original radioactive material is left after 15 half-lives? This is one that I wouldn't want to do table-based. 0 half-lives, 100%. One half-life, 50%. Two half-lives, 25%. I mean, this is going to take forever if I was going to do that. So I'm going to just go straight to the equation. Y equals 1 over 2 to the 15th power. Type that into the calculator. 1 divided by 2 to the power of 15, and you get the answer 0.000030518, or better said, 3.0. I'll stop there. 3.05, 1, 2, 3, 4, 5. You get smaller by 5, so times 10 to the negative fifth. So that is how much of a sample you would have of the original after 15 half-lives. Not everything's created equal. Once again, half-lives range from billions to really seconds, but this one stops at like years. But there are many things that have half-lives of seconds. They just don't stay for that long. They just keep on breaking down. Okay, here's another example. We start with a 400-gram sample. How many grams would remain after 3 half-lives? Well, this is not a bad one to figure out based on a graph. If I wanted to go straight ahead and solve it, 400 grams at 1 half-life. Sorry, no, that's 0 half-lives. Don't do that. That's a common mistake people make. At 0 half-lives, it's the whole thing, 400 grams, 1 half-life, 2 half-lives, 3 half-lives. Type in your calculator 400 grams, divide by 2, equals, you get 200 here. Divide by 2, you get 100 here. That's something you can do in your head, but if you don't want to think about it, divide by 2 again, 50 grams here. So here's the answer just using a table. Now if I want to do the math, I could figure out, okay, what fraction is going to remain? 1 over 2 to the nth power, and so y equals 1 over 2 to the third. I do that in the calculator. 1 divided by 2 to the power of 3, and I get 0.125. And now I can take that and I can multiply it by my original sample. So 0.125 times my original sample is 400, and I should get the same answer, times 450. So 2 ways, that should be 50 grams. 2 ways to accomplish this. You can do it graphically. Just write down 0, start off with the 0 being the whole, and then 1, 2, 3, 4. Just count how many half-lives and go from there, or sometimes it's easier just to do it mathematically. Fraction remaining. Okay, so here's another example. A radioactive sample has a mass of 56 milligrams and a half-life of 30 minutes. How much of the sample remains after 60 minutes? Well, here it's taking you to another step. Okay, how much is after 60 minutes, but the half-life is 30 minutes? What's going to be useful here is to figure out how many half-lives occurred. So that's where you go to the T1/2 equals time over n, and I want to solve for n, so I'm going to have to rearrange this. N equals G over T1/2. And so I take the total time. Really, what I'm doing is taking the total time divided by 1 half-life, and I find that I get 2 half-lives. So if I want to figure out how much remains, I can do it graphically. 0, at 0 time I have 56 milligrams. Here we have milligrams. So that our unit would have to be milligrams at the end. 1, 2. So after 1 half-life, type in 56 in your calculator, divide by 2, you get 28 milligrams. 2 half-lives, divide it by 2 again, you get 14 milligrams. And so there's our answer, 14 milligrams. Now I could do it the fraction remaining way, y equals 1 over 2 to the second, or 1/4, and then you multiply that 1/4 by the original sample, which was 56, and you would get the 14 milligrams either way. So 2 ways to accomplish this. I don't care in my class, at least in this class, how much detail you go into if you do it graphically or if you do it mathematically. Either way will be fine. Here's another example. An unknown radioactive material has half-life of 4,000 years. How much of the sample remains after 20,000 years? Okay, so total time 20,000. For half-life is 4,000. Get your answer there. 20,000 divided by 4,000, and you get 5 half-lives. So from here, you can do it two ways. Once again, 0. Sorry, I'm writing the numbers up top or down the bottom. I switched it back up. 2, 3, 4, 5. Okay, so you have a sample. How much of the sample remain? Okay, here we can make it 100%. Careful to start at 0 with the whole amount, and then you can go from there. You get 50, 25, divided by 2 every time, 12.5, divided by 2, 6.25, divided by 2, 3.125%. And if the fraction, it would be 0.03125, but you have 3.125%. If I did it mathematically, I can figure out the percent remaining. That way, y equals 1 over 2 to the 5th. So either way would work. You would have to start by figuring out the number of half-lives, and then either plugging it in or doing it graphically from there. Okay, here we have example E. A sample of radioactive material with a mass of 32 grams decays to 1 gram in 18 minutes. What's the half-life of the isotope? I'm going to start by not doing it in a very mathematical way. There's more, if you're willing to do a little bit of math, there's other ways to go about this. But let's just figure out how many half-lives we have to get from 32 to 0. So 32, cut it in half, you have 16. Cut that in half, you have 8. Cut that in half. Right? So third half-life, you have 4, cut that in half, you have 2, cut that in half, you have 1 gram. So 4, 5, that's going to be 5 half-lives. So if you're trying to determine what the half-life is, if you had 5 half-lives and it occurred in 18 minutes, then you go to the half-life equation. Well, here we have the time of 18 minutes and 5 half-lives occurred. So you take your calculator, 18 divided by 5, and you get 3.6 minutes per half-life. Okay, just a little bit more about radioactivity. It's used, most people know about some of the uses for detection of some sort. It could be to detect cancers. It can also be used to treat cancers. There's a lot of radioactive materials can damage newer cells, and cancer cells tend to be newer than the more mature cells. And we can use it to determine the age of rocks. If we know that something living was in that rock, we can determine how many, based on the half-life of whatever we're looking at, carbon-14 is often used, we can determine how many times it went through its half-life since that object, that thing, whatever organism it was, died. So the organism dies. While it's living, it's eating and continually adding more carbon-14 to its system at a rate, but once it dies, it's no longer eating, so it just starts decaying. You can use that process in the half-life to figure out how long that rock may be, or fossil may be. Natural transmutation is just spontaneous. It occurs without you having to do anything, but sometimes you don't want to wait around, so you can actually cause it to happen, and that's called artificial transmutation, not natural transmutation. In that case here, you could bombard something with, here you're bombarding it with alpha particles, and then when you bombard this 14.7, so it's nitrogen 14, you're bombarding the nitrogen 14 with this alpha particle, you're giving off these hydrogen protons, and what you're left off with, you got to do the same thing. You've got to balance the equation. So 7 plus 2 should be, we've got 9 down here, we've got 18 over here, and so let's see what's left over. So here should be 18 up top, well 17 right there. You should have 8 down the bottom, and if you take a look at the periodic table, anything that has 8 protons would have to be oxygen. So this is what you'd be left off with. Here's another transmutation, bombarding this is actually the same one we just did. So 17 over 8 oxygen. This was first done by Ernest Rutherford. also helped us determine what the makeup of a nucleus was. Nuclear fission, there's two types of things you often hear about when you have nuclear reactions. Fission and fusion. Fission, think about breaking apart. Fusion, when I hear the term fusion, I think things are coming together. So fission is the opposite. Fission is breaking apart. And so you take heavy nuclei like uranium. There's certain uranium that works the best. You take the heavy nuclei, you make sure there's a lot more of that uranium around because you want a spontaneous generation. You bombard it with here you're bombarding it with neutrons. When it hits the uranium, it splits it. So it splits this uranium, and when it splits the uranium into two other elements, that splitting releases 3 more of those neutrons, which are going to go and hit more uranium. As long as you have enough uranium around to cause this to spontaneously occur, so these things need more uranium to hit, then the reaction will just occur over and over and over, and a lot of energy can be released, because every time you remember the equation, E equals mc squared, the m stands for mass. Every time this occurs, you lose a little bit of mass, and that mass turns into energy. So the critical mass is the minimum amount of isotope you need, that uranium or whatever you're using, to have the chain reaction, to keep it occurring. Problems with fission being used, and this is what we do normally. Right now we use fission in our nuclear reactors, is that the half-life of uranium is 713 million years. So all we can do is pretty much store this. It's not going to, there's going to be many and many millions of generations before what we're using today to produce energy is ever going to decay. It's still going to be dangerous. So it's just storing. And we can send it off to space. Who knows what will happen there? But it's just there's just no place for that. So that's a main problem with fission. Besides that, it's considered pretty natural. You don't have the carbon gases that are released from normal burning. Here you would most likely be using it to heat water or turn a generator with steam power. Fairly clean, except for that whole radioactive waste. You need to find a way to put that somewhere, and often we dig a hole and store it in places. That's our options right now. Nuclear fusion, this is the power of the stars. This is what occurs on our sun and any star out there. And this has a tendency to release even more energy than fission. The problem is it releases so much energy, it's really hard to be contained. So this would work great, and also you got yourself helium. You might have a little high voice. Besides that, it's not really going to do much. And nothing that's really too dangerous for us. This is something that we can handle if we could figure out how to contain this reaction. If we can contain this reaction, but it gets so hot, it breaks down the walls, and we can do it, but it costs more money to create the containers than it would be to create energy in other ways. So the biggest problem with nuclear fusion is that it's just we can't contain it. And people are working on magnetic devices to hold that reaction. There's a lot of different things. Lockheed Martin in the past couple of years said that they had something they were working on. They made it work. We might hear more in the future. So 10 times out of fission released from this reaction. And just can't sustain it. And that's that.